Have you ever really thought about what it takes to drill a hole miles deep into the Earth's crust? I mean, it is just an absolutely incredible feat of engineering. But what kind of raw, brute force does it actually take to make that happen? Well, the answer is a lot. And it might just surprise you.
Okay, let's get right into it. Today, we're going on a deep dive, and I mean that literally, into the power system of a modern drilling rig. We're going to follow the energy, right from the fuel tank all the way down to the drill bit, to really understand the incredible forces at play here.
So here's our game plan. First, we'll look at the basic anatomy of a rig. Then, we'll get into the massive scale of its power source. After that, we'll see how all that power gets put to work, and finally, we're going to put it all to the test to answer one really critical question. How much of that energy is actually doing the work?
To really get started, you've got to understand that a drilling rig isn't just one single machine. Nope, it's more like a symphony of complex, interconnected systems all working together for one purpose: to drill a hole deep into the ground.
A typical rotary rig is broken down into these 6 main components. You've got your systems for hoisting, rotating, and circulating fluid, plus, of course, systems for control and monitoring. But here's the thing. None of them, not a single one, can work without that very first one on the list, the power system. And that's going to be our focus today.
So, when we talk about the rig's power system, the beating heart of this whole operation, what kind of numbers are we really dealing with? The scale of it is actually pretty mind-blowing. For a large rig, we're looking at a total power requirement of up to 3,000 horsepower. Now, to put that into perspective for you, that's like harnessing the power of about 20 high-performance sports cars, all of them just dedicated to this one single task. That is a ton of power.
And you know, that power isn't one size fits all. It scales with the challenge. So for a well that's less than a mile deep, a couple of engines and about 1,000 horsepower will get the job done. But if you want to push down over 2 miles, yeah, that's when the rig needs 3 to 4 of these monster engines, generating that massive 3,000 horsepower.
Okay. So we know how much power is needed, but how is it actually made and then delivered to all the places it needs to go? This is where we get into the nitty-gritty of the power system itself.
You know, the technology has come a long way. The earliest drilling rigs, they were powered by steam engines. You can just picture it, right? Very industrial revolution. But today's modern rigs have moved on to a much more efficient and powerful source: these massive internal combustion diesel engines.
Now, once those engines are roaring, there are basically 2 main ways to get that power to the rig's components. You can use a mechanical or direct drive system, think shafts and gears, a lot like in a car, or you can go with a diesel-electric system, where the engines generate electricity that then powers motors all over the rig.
And this brings us to a really crucial point. We're burning fuel to create work, but how much of that fuel's potential energy actually becomes useful work? That concept is called thermal efficiency, and it is the single most important metric for engine performance. It's really just a simple ratio, work out versus energy in.
So with up to 3,000 horsepower at our fingertips, where is it all being spent? It turns out not all operations on the rig are created equal when it comes to chugging down energy.
So here's the power breakdown. While some energy gets used for rotating the drill and other basic functions like lighting, the vast majority of it, the lion's share, is consumed by just 2 systems: the hoisting system for lifting thousands of feet of pipe out of the ground, and the fluid circulation system. When it comes to power, these 2 are the undisputed heavyweights.
And this brings us to the final, and I think most critical question. We're burning all this fuel to generate this immense power, but how efficient are these engines really? Let's run the numbers and see what percentage of the fuel's chemical energy actually gets transformed into mechanical work.
All right, to figure out efficiency, we first need to measure the work out. That's the actual power the engine is delivering. Conceptually, it's pretty simple. You just multiply the engine's rotational speed by its rotational force, which we call torque. That gives us 1/2 of our equation. Next up, we need the energy in. And this part, it's all about the fuel. We measure how much potential energy we're putting into the system by looking at how fast we're burning fuel and its energy density, which is basically how much punch is packed into every single gallon of diesel.
Okay, let's put it all together with a real-world example. So we've got an engine with a known torque and speed, and we know exactly how much fuel it's burning every hour. The question is, what's its power output, and more importantly, what is its actual efficiency? So, when we actually run the numbers for our example engine, here's what we find. The work out is about 398 horsepower. Okay, but the energy in from the fuel being burned, is the equivalent of over 1,100 horsepower. The difference there is just huge. So dividing one by the other gives us our final answer, 0.354.
That's right, the overall thermal efficiency is only 35.4%. And what does that mean? Well, it means that for every single gallon of diesel we burn, nearly 2/3 of its potential energy isn't turned into useful work. It's just lost. It's waste heat. An absolutely incredible amount of energy just dissipating into the air.
So the huge takeaway here is that while these machines are just immensely powerful, they're also a testament to the fundamental challenges of energy conversion. And it leaves us with a really fascinating question. If today's pinnacle of drilling power wastes almost 65% of its fuel's energy, what kind of innovations will define the more efficient, more powerful systems of tomorrow?